Our second proposition concerns the invertibility of elements in ZP. It has two parts. The first part states as follows. For an element in ZP to be invertible, it is necessary and sufficient that it is not divisible by P. We're going to first establish the statement for A sub n's, and then the case for ZP will follow easily. In AN, remember AN is Z mod PNZ, and Z sub P is the inverse limit for A sub n's, or projective limit of A sub n's. The forward direction is easy. For the forward direction, suppose an element is divisible by P. Namely, if xn is equal to P times yn for some yn in AN, then if we multiply both sides by P to the power n minus 1, we will get a zero element. But what does this relation tell us? This forces that xn is not invertible. Otherwise, we multiply both sides of this equation by xn inverse. Then we will get Pn minus 1 is equal to 0 in AN. But we know that A sub n is Z mod PNZ, so this guy is not equal to 0. So this is absurd. Therefore, xn must not be invertible. And this completes this forward direction. For the backward direction, if xn in AN is not divisible by P, then if we view xn as an integer, this integer is coprime to P. And by elementary number theory, you know there exist integers yn and zn such that yn xn plus znp is equal to 1. This is so-called Brazos theorem. And this implies x and yn equal to 1 minus p times zn. Remember, our goal is to find the inverse to xn in AN. And now we're going to find it. If we multiply both sides of this equation by this element, we realize that the right-hand side, by the classical formula from algebra, is equal to 1 minus p to the power n, zn to the power n. But what is this guy? This guy is just congruent to 1 modulo Pn. Therefore, modulo Pn, we have found an inverse to xn, which is this thing. So in AN, xn inverse is represented by this integer. So in an, xn is indeed invertible. Now the remaining question for us is, after completing the case for an, how do we pass it to Zp? Remember, Zp is a projective limit or inverse limit of ans. And the elements in Zp are formed as the compatible sequences from ans. So to pass from the case of an to Zp, it suffices to show the following. It suffices to show that if you have a compatible sequence in Zp, and each x of n is invertible in an, then the sequence where we take inverse of each component is again compatible. It suffices to show this. But this is easy. This is easy because if phi sub n plus 1 of xn plus 1 is equal to xn, which is the compatibility condition in here, then phi sub n plus 1 of xn plus 1 inverse, by the definition and property for the ring homomorphism, this is equal to phi sub n plus 1 of xn plus 1, the whole thing inverse, which is just xn inverse. So phi sub n plus 1 of xn plus 1 inverse is equal to xn inverse. Therefore, this sequence is again compatible. And this gives a well-defined inverse in Zp. So this sequence is not just in the infinite product, but also compatible. So it is in Zp. And this completes the part A of this proposition. Now let's look at part B. If we put together all the invertible elements in Zp, which is a ring, then it will form a multiplicative subgroup. And part B of this proposition states that every non-zero element from Zp can be written uniquely as a product of some power p and another element from this subgroup. And elements in U are called p-adic units. Now let's prove this. For any non-zero element in Zp, we observe that there always exists a largest integer such that the nth component, xn, is equal to 0. And here we have a convention that x0 equal to 0. So there is always at least one xn such that xn equals to 0. So we are not dealing with the empty set. Now why there's always a largest integer satisfying this? This is because otherwise there are infinite many n's with xn equal to 0. Then, by the compatibility of the sequence, we must have x itself equal to 0. Because each component of x would become the image of a 0 at some position. So there always is a largest integer such that xn equals 0. And now we're going to invoke our proposition 1. Since xn, which is epsilon sub n of x, is equal to 0 in an, we must have, by proposition 1, x being in the kernel of epsilon sub n, which is equal to the image of the multiplication by Pn map. So there exists U in Zp such that x is p to the n times u. We are using the exactness here because x has its nth component mapped to 0, so it is in the kernel of this. So it must also be in the image of this. So there is a pre-image here, which we denote by u. And we also know this multiplication by Pn is injective, so this pre-image must also be unique. So this is also unique. Now, since this n is also the largest integer with xn equal to 0, we must have that this u is not divisible by p. Otherwise, you can always factor out a factor p and change this to x equal to p to the n plus 1 times some u prime. And this will imply that xn plus 1 is equal to 0 in an plus 1, contradicting to the maximality of n. So p cannot divide u. And because p cannot divide u, by the part A of our proposition, we must have u is invertible. Namely, u is in this capital U, the subgroup of all invertible elements in Zp. And this gives the existence of this decomposition. Then what about the uniqueness? The uniqueness is clear. Suppose x has two decompositions, Pnu and Pn prime u prime. With n prime non-negative integers and u prime in Zp, which are both invertible. If n is not equal to n prime, say n is less than n prime, then u is equal to p to the power n prime minus n times u prime. In particular, this will imply that P divides U because n prime is strictly bigger than n, which is same as saying that U is not invertible, contradicting to the assumption. If n is equal to n prime, then we have the decomposition x equal to pnu prime. Then we must have u equal to u prime. That is because this u, once we have fixed n to be the same, must be uniquely determined from here because of the injectivity of the multiplication by Pn from proposition 1. And this verifies the uniqueness and therefore the whole proof.